We've just talked about quantum numbers. The four quantum numbers of N, L, M sub L, and M sub S. Let's look more at the orbitals. And we're getting those from the L quantum number, the angular momentum quantum number, that when they have the values of 0, 1, 2, and 3, have the letter designations of S, P, D, and F. So let's look at L is equal to 0. That means we've got an S orbital. And I invite you to look in your textbook at more complicated diagrams, in-depth diagrams of all of these. And what we're trying to do is show the probability of finding an electron. Remember that the atomic orbital doesn't really have a well-defined shape. It's a wave function. It's characterizing the probability of finding an electron when we square it. And so that probability extends from the nucleus all the way out to wherever, to infinity. And so what we're sort of doing is describing some shapes that would give us the 90% probability of finding an electron at any given time. So we've talked about these wave functions, and we've talked about standing waves. And so in your mind's eye, the simplest case, and this is a gross oversimplification, but if you took a half wave, and this is in 2 dimensions, and you rotate it around an axis, in 2 dimensions you would generate a sphere. And it's 2 dimensions a circle, in 3 dimensions is a sphere. So 2 dimensions, and let's rotate in 3 dimensions, and it will give us a sphere. And so that's the general shape of a s orbital, or that they're spheres. If L is equal to 1, we're now talking about p orbitals. And these wave equations that you can think of being as trigonometric equations. So if we had a wave that looked something like this, and we rotated it in 3 dimensions around this axis, we wind up having something that looks like this. And so there was just a single sphere, if you will, for an s orbital. This p orbital has 2 lobes to it, a right half and a left half, if you want to think about it that way. Remember, this is in 3 dimensions. And so once again, I invite you to look at your textbook for a better diagram of this. For s orbitals, if L is 0, M sub L had to be 0. So there's only a single s orbital for any value of n, the principal quantum number. Whereas for L, the M sub L values can be -1, 0, or +1. So now we've got a trio of possible p orbitals. These p orbitals are referred to as being degenerate. And the bad joke that I always use about this is, this degeneracy is not like finding someone drunk in the ditch on Friday night. That's a whole different type of degeneracy. This degeneracy means that they have equivalent energies that you can't tell them apart, other than when you stick them in a magnetic field, and hence where the M sub L designation comes from. And so if we were to take these 3 p orbitals and put them on Cartesian coordinates, putting them all together, we would come up with something like this. So we could further label these orbitals as being px, py, and pz. How about d orbitals? So remember, L values of 0, 1, 2, 3 gave us designations of S, P, D, and F. So now we're talking about L equals to 2. That means the m's available values are minus 2, minus 1, 0, plus 1, and plus 2. And the d orbitals are going to be even funkier looking. The s orbitals were just like a sphere. The p orbitals had 2 lobes to them. And the d orbitals, there are 4 of them that sort of have this type of shape. Once again, I invite you to look at your textbook to see it in more detail. There's another one that has this type of shape. And so there are 4 of them that are sort of like a clover leaf, a 3-dimensional clover leaf, that we could refer to as being the d x squared minus y squared, the d xy, the d xz, and the d yz. These are the 3-dimensional clover leaves. Whereas there's a single one that's called the d squared, dz squared. It's sort of like a p orbital with a donut around it. So it's a p orbital with a donut. Now these shapes, once again, they're trying to describe out these 3-dimensional spaces where we have the 90% probability of finding an electron. An electron doesn't know that it's in a s orbital or a p orbital or a d orbital. It's just doing its thing. We've come up with these orbitals, these quantum mechanical descriptions of how electrons are arranged in atoms to try to explain the behavior of atoms. So let's talk a little bit about the energies of these atoms, or these orbitals. And in a hydrogen atom, if we let this y-axis be energy, let it be increasing as we go up. If we let these boxes represent the orbitals symbolically, we've got our 1s orbitals, and then we have 2p, with 2s and 2p, and 3s, and 3p, and 3d, and so on. Now, if we put these into a mini electron system, anything other than hydrogen, these energy levels are going to split further. We've got our lowest energy will be the 1s, then the 2s, and then the 2p's will be a little bit higher energy. Then will come the 3s, and the 3p's. Then actually the 4s is of lower energy than the 3d's, and so on. And so those are the orbital energy levels in a multiple electron atom. And so as n increases, the orbital energy increases, and also increases with the value of L.